Hi, everybody, ladies, gentlemen, non-binary. Good morning, good afternoon, and good evening, wherever you are in the world. I am so happy that you can join us here today. My name is Amelia Thompson, your host of the Worth Electronic webinars. Today, we are welcoming back a presenter that we had earlier this year. Timur Uladag is the product manager for our Magic product division in Worth Electronic. Today's webinar is improving the EMI performance of isolated power modules. If you have any questions during today's webinar, feel free to ask them in that questions box, and our presenter will answer them at the end. A lot of people do like to test out the questions box, making sure everything is working. So if you want to test it out, feel free to say hello, tell me how you're doing today, maybe any projects that you might be working on. Now, if your questions don't get answered, if you want to go into detail about a project, or if you just think of them a little bit later, simply email us at here4you, that's here, the number 4, YOU, at we-online.com. As a reminder, because you registered for today's webinar, you will automatically receive the recording and the PDF of the slides when they become available. It might take roughly 24 to 48 hours, depending on how fast our internet connection is. And don't forget to register for our next webinar. On September 1st, we will be presenting all about capacitor selection, but that one is in Spanish. And then our next English webinar is September 8th, use of Magic Power Modules as adjustable constant current sources. Register online at www.we-online.com/webinars. And of course, all of our webinars are made possible thanks to our exclusive sponsors over at Digi-Key Electronics, right? Our neighbors in Minnesota in the United States. I also want to remind you about our newest podcast called the Worth Electronic What's Up Radio Podcast. That's What's Up, WATTS. Each week I bring our application notes, our blogs, and our webinars, press releases to an audio format. You can find us on Spotify, iTunes, Google Podcasts, anywhere that you want to listen to a podcast. You can find the Worth Electronic What's Up Radio Podcast. And now we're going to in today's Worth Electronic webinar with Timur Uladag, improving the EMI of isolated power modules.
So, can everybody hear me? Wait. So, I hope everybody can understand me loud and clear. My name, as Emilia mentioned, is Timur Uladag. I'm working since October 2015 as a Magic Power Module marketing project manager for the Worth Electronics. Today, I will highlight the topic of EMI of an isolated power module and a workaround for common mode noise. Today's webinar will cover some topics. We will start with an introduction about some myth around common mode noise. During the EMI basics section, we will summarize the needed EMI knowledge for this webinar. With this knowledge, then, we can apply the Kirchhoff's law to the common mode circuit. To prove that the rule of thumb that we have worked out works fine, we will make a numerical example calculation for the Y cap with one of our isolated power modules. To round off this topic, we show you the concept of our predefined filters for our power modules. Let us first talk about some fairy tales around common mode suppression. In third place of the list is common mode noise, interference suppression are rather difficult to understand. In second place, we have common mode interference suppression is more of a try and error process. third, and let's say the most common myth I heard is common mode interference suppression only works with common mode chokes. But to be honest, that's completely wrong. The truth is that common mode interference suppression is not a rocket science. The knowledge about the basic electrical interactions and Kirchhoff's law are all you need to set up a common mode filter. That's it. To better understand the common mode noise topic, we need to understand first the application where isolated power module is used. The schematic shows the basic structure of an industrial plant in the field of automation. Industrial applications are known for long connecting lines between the separated parts of the applications. Due to the spatial extensions, the length of these connection lines can be in the range of tens of meters. These here. Therefore, ground loops are a common problem. The isolated power modules here can interrupt unwanted ground loops and isolate from disturbances that come from the DC bus. To be well prepared for the next steps, because now we are getting deeper in technical stuff, let us make a short wrap up about the common mode and differential mode and its basics. What you have to understand is the differential mode flows in the same direction as the switching current. As you can see here, the green one. It goes in and out. The common mode current flows on both supply lines in the same direction. Here in, here in. The return path of the common mode current is the ground connection here, about this coupling capacitor. So it flows out and whoop, in here again. Here we have two simplified examples of real circuit constructions to make the setup of a parasitic capacitance clearer, because this is one of the biggest points that is very hard to understand, how a parasitic coupling capacity is built up. Example one, if we have, let's say, an input or output cable for a DC converter, we will have two separate wires with different potential, with a distance to each other. Therefore, we will have here a parasitic coupling capacitance between them. Example 2, also a single wire and a plane where we have different potential will lead to a parasitic capacitance between them. The application from the beginning is only one of many other applications. There are uncountable out there. Therefore, it is nearly impossible to use one strategy for the common mode filtering that applies to all applications. In order to ensure comparability, a standardized framework, let's say experimental setup, must be used so that you can compare each filter to the other. The structure based here is on CISPR 32, and it is sufficient here to be able to compare the effect of the different filter components with each other. The setup here shows the EMI measurement setup of an evaluation board of our magic power modules. The structure and the power module itself have been expanded to include the components relevant for common mode considerations. The origin of the common mode noise are the switching elements. This one here and this one here. The noise spreads over the dV by dt that pushes the current through the interwinding coupling capacitance of the transformer from the primary side to the secondary side. The return path will then be over the coupling capacitance through the ground and back to hear the listen. The output and input wires act here as an antenna for the common mode noise current, which leads to here, for example, to radiated problems. In reality, the module is connected to ground on the primary side, for example, minus Vin. Then we talk here about an unbalanced system. Also, the cable lengths here of the input and output are much smaller in reality. So my computer is breaking down. Wait, sorry. Amelia, I think we have got a small problem. Wait. It's coming. The dominant, sorry for that, the dominant coupling mechanism underlying here is the capacitive one. Therefore, we can simplify the schematic for further considerations. The source are, as I told, the switching elements, like the BGTs on the primary side. If the potential now change in relation to each other, an interference current, I noise, begins to flow across the parasitic capacitance here and here. The path is the interwinding capacitance of the transformer CK. The topology that we use here for our power module SIP4 is a self-oscillating push-pull converter. The switching action is driven by the saturation of the used toroid transformer. The switching current increases as long as a toroid saturates. And at the point where the toroid saturates, the switching takes action. The switch voltage here, marked in blue, leads to a certain dV by dt, which is the source of the common mode current. The detailed plot here shows the correlation more detailed. The switching contains of switching itself, what we have here, and the resulting ringing here. The ringing, as everybody knows, is characterized by higher frequency. The noise current and we're looking at is mainly driven by dV by dt. This is the capacitive effect. Effects based on dE by dt will not be covered in this webinar. A transformer is not a 100% barrier for the electric current. That means a real transformer always has parasitic capacities due to its primary and secondary winding structure and the resulting layer structure. It depends on the plastic foils you use, or if you use magnet wire or triple isolated wire, if you make it one chamber or two chambers. So all this has a lot of effects. These interwinding capacitances are formed between the plus primary here and plus secondary but also from minus primary to minus secondary. Due to the center tapped structure we have here, we also have it across from minus to plus or from plus to minus. In general, we have three methods to solve EMI issues. The most effective method is to solve the problem where it is created. That means inside the power module, followed by keeping the interference current away from the meter. Here, the listen. Last but not least, if method 1 or 2 cannot be chosen, to damp the noise so that the measured value at the meter is under a certain value. Here, we will take a closer look to don't let the noise reach the listen. For common mode noise reduction, we have to separate between PCB level and system level common mode noise reduction. Snap ferrites have, let's say, a typical value of 100 megahertz. And so that means you can use them for a system level if you put them on the cables. If you go for a, let's say, PCB level reduction, you can use a chip bit ferrite. It has a low attenuation, but it is extremely cheap, but you have always losses. Or you can use a bridging capacitor. It has a good attenuation, is also cheap, but you have to be aware because it is from primary to secondary, so there might be a safety issue. This is what we're talking about today. Let us now explore the meaning of don't let noise reach the listen. The schematic shows a simplified version here of the setup we have already talked about. The schematic here shows both noise current loops. As we already know, the common mode current flows through the power module and closes the current circle via ground. This is marked here with the 2. So it goes in, through, out, to the coupling capacity and back. The current loop here, marked in blue, the 1, shows an alternative loop. The current flows through the power module and then takes a branch around the power module. Goes in and a branch, let's say a short circuit we have here. But why should the noise current choose the branch circuit? The branch has to be, let's say, more attractive for eye noise than path 2. The current always takes the easiest path. This is what you learn at the first day of any study in terms of electronics. That means the branch has to be less impedant than the existing one. If we take a look on the requirements for the branch elements, it is obvious that a capacitor is a component of choice, because as higher the frequency goes, as lower the impedance will be. Let's get now to the rule of thumb for our Y cap. The big idea behind the rule of thumb is to compare the circuit without branch and with branch. That means we compare the voltage drop with Y cap with the voltage drop without Y cap. The ratio expressed in dB is then the attenuation A we want to have. to get the value of the bridging capacitor we need, now we, let's say, redraw the known schematic to a more simplified electrical equivalent circuit, to which we can then apply the known Kirchhoff's laws. First, we have here the circuit without Y cap. The circuit on the left can be redrawn to the simplified equivalent circuit on the right. The voltage source, Vs, here stands representative of all common mode interference voltage sources in the power module, because there are some more. You not only have the BGTs, it's all switching elements. So that means also the secondary diodes that switch are also included. The listen here, the parasitic capacitance we have here, and the magic power module here are all connected in series. So we can calculate V1 by using the known formula of a voltage divider. If we now rearrange the basic equation for the series circuit according to the voltage V1 we are looking for, we get the formula as shown here. This equation represents the voltage drop over the listen, this here. Second, the circuit with a Y cap, here and here connected. This is why I have marked 1 and 2 in green, so for better understanding you can see where it is connected. The circuit on the left can now be redrawn again and simplified from here to here. And the voltage source Vs here represent all common mode interference voltages in the power module. The circuit now is a mixture of a series and a parallel structure. Z1, the Y cap here, is connected in parallel to the listen and the parasitic capacitance here and here. So this here is the parallel connection. The parallel connected branch is then in series connection to the magic power module, here in series connection to the power module. If we now rearrange the basic equation for the parallel circuit and the series circuit according to the voltage V2 we're looking for, we get the formula as shown. If we insert now the equation for V1 and V2 into our equation for the attenuation, we get the expression we needed. So, sorry, the system hangs again. Here, we have here the example calculation for the simplification of the equation. To make the equation more user-friendly, let us make a quick, let's say, numerical example. If we put in the values we have, then we get here a linear attenuation of 0.168. If we now here take a closer look to the values, we can see that the red highlighted ones here, here, and here are all nearly 1000 ohms. Some are a little bit higher here and here, or lower here, but they are all roughly 1000 ohms. The basic equation can now be more simplified if we shorten the red marked values out, this one's here. We can cross out 1 here also, because it is more than 6 times lower than 212 ohms over 24 ohms. So the remaining equation is now A is ZY over ZK. The new iteration is 0.16. And if you look on the delta A, it is only 0.42 dBs, which means the simplified result is pretty close to the one of the longer equation. With this short equation, we will now do an example calculation of our real power module. We have here a conducted EMI plot from the SIP4 power module 12 volts to 5 volts. To start, we have to choose the desired attenuation. That means the damping that we want to have. We take here 15 dBs in the range from 4 megahertz to 30 megahertz. From 4 to 30 megahertz. The value for the interwinding coupling capacity we can get from the datasheet of the power module. The value we have here is usually given as a maximum value. That means if we take this, we are talking about a worst case value. What is also very important, this value is typically measured at 100 kilohertz, but it is stable or nearly stable up to a, let's say, region of the beginning of gigahertz. So we can take this data sheet value for our calculation. If we look now on the setup of the measurement, we can see that the real coupling capacity is somehow a mixture between two parallel planes and one conductor parallel over a flat surface. Here and here. Regarding the values for the coupling capacitance, the difference here is not so big. So we can choose a value between 10 and 20 picofarads. That also fits pretty good with our value we had for the example to simplify the equation. So we get now an attenuation of 15 dB. We need a 470 picofarads Y cap. So far, so good. This is the real theory what we're talking about here. Let us now check if the theory can withstand the real world test. Therefore, we put in the value and make a measurement again. The conducted EMI plot you have here shows a varying Y cap. so that you get more the feeling about in which region it can go from 0 picofarads up to the calculated one for 470 picofarads. As higher the Y cap, as higher will be the resulting damping. Remember, we calculated 17.2 dBs attenuation for a 470 picofarads Y cap, but the real measurement shows an attenuation of nearly 19 dB. It's only a delta of 2 dBs. But how does it come? It's the value of CK that changes the real attenuation. Datasheet gives only a max value. Here we have not 75, but if you recalculate it, somehow 60 picofarads as in the winding coupling capacity. The ideal impedance behavior of the 470 picofarads capacitor is as showed here. At low frequency, the Y cap is high impedant. Here we have got 3 kilo ohms. If we now increase the frequency from, let's say, 100 kilohertz to megahertz, you can see that we have got a linear decreasing value of the impedance. So it goes down from 3 kilohertz to, from 3 kilo ohms, sorry, to 10 ohms. What we have calculated up to now for the bridging capacitor was based on the ideal equation for XC. We have neglected here the inductive component as well as the ESR. If we now compare the theoretical impedance curve with that of a real Y cap, I did this here with our Red Expert tool. I took a 470 picofarads MLCC. Then you can see that this is a pretty good match. At 100 kilohertz, we are at around 3 kilo ohms. And if we go down to 30 megahertz, we are at about 10 ohms. So this is a perfect match with our theoretical consideration. If you want to have it the easy way, then we have built up, we call it, let's say, application-specific EMI filters, a small bag here where you can have all the parts in so that you can have an easygoing filtering for the isolated power modules. You have got a small card that shows everything you have. You have got the bill of materials, and here a lot of more information you can get from our online catalog. So far so good. I hope you enjoyed the webinar. For now, I'm done. If you want to have support, if you have got some questions, if you need any help, please do not hesitate to contact us. The design-in support, if it is electrical or EMI wise, is 100% free of charge. If you have got a layout and you want to make a quick check on it, please send it to us. We can make a design-in support for you. We can help you with your EMC filter calculation. As I told, the layout review can also be done. And we also have a very good tool that it is included in Red Expert to make a thermal design consideration about the needed space for the power modules for optimum heat spreading. Thank you. I stay here if you have got some questions.
Okay, thank you very much for presenting today. It looks like we do have a few questions rolling on in. And again, as Tamir mentioned, please feel free to ask them in the questions box. Our first question is, can I use every high voltage MLCC as a bridging capacitor?
Yes, of course, you can use it. You have to take only, let's say, aware of if you're using it for, let's say, functional isolated design, where you don't have any, let's say, electric shock protection, or if your design is to be preventing from an electrical shock, then you have to choose some different Y capacitors from us. But yes.
Okay, excellent. Our next question here. For which isolated power module are the filter bags available?
The filter bags, the predefined, are available for all our isolated power modules. So for everyone, you can get it. Go please to the online catalog, take a look on it. But if you don't want to make this effort, send us an email and we will help you. We will more than, let's say, happy to help you here.
Absolutely, and there is going to be a poll here shortly asking if you are interested in free samples, and if you are interested in free samples, then feel free to let us know. Our next, oh, there it is. Okay, our next question here: why is it so hard to determine the coupling capacitance to the environment?
Good question. It is so hard because it depends on many parameters. It depends on, let's say, the structure of the two electrodes. That means if you have got a wire over a plane or two wires to each other, if the wires you have are enameled with let's say varnish, or if there is a rubber tube. And so it is not so easy. So we can say it is more of a rule of thumb to get to good values.
Okay, looks like we do have a few more questions rolling in. As a reminder, if you think of a question a little bit later, or if you believe it's too technical and you really want some really great advice, feel free to ask the question here and we will reach out to you later, or email us at hereforyou@we-online.com. We'll make sure that you're all taken care of, even if you do need the free samples or the technical assistance, we're there for you. Our next question: does the use of a bridging capacitor influence the common mode radiation?
Yes, it will influence, because the common mode current is then not able to flow on the output and input lines. So if there's no current on the lines, no switching current on the lines, common mode current, then there will be no radiation. So you will definitely see it in your radiated EMI plot that Y cap is working.
That is great news. I'm pretty sure I know the answer to this next one, but does Worth Electronic have any plans for developing isolated magic power modules?
We have developed a lot of isolated power modules, and you can see them all in the online catalog.
Excellent. We'll be sure to actually include a link in the follow-up email that does include the video on demand as well as the presentation. You're going to be receiving that from here for you at we-online.com because you registered for today's event. We're going to finish up the questions here. We do have a few more rolling in, but we'll make sure to answer those after the webinar. What is the best value on, this one might be, he says it might be too technical, but what is the best value on capacitor between first side and second side with isolated power modules? And what is the effect for reducing conducted emission?
The best value is very hard to determine, but as a rule of thumb or from our experience, if you start with 220 picofarads and choose then 470 picofarads for an isolated power module in a 1 watt region where you have got, let's say, 50 to 80 picofarads as a coupling capacitance, this is a good starting value. And then you will see it, let's say, starting megahertz region in the conducted EMI plot, that the spikes are going to be damped.
All right, excellent. We're going to wrap up the questions here. Again, we will be answering them after today's webinar. I want to thank you, Tamir, for presenting for us today.
Thank you, Amelia. So,
and thank you everybody for joining us. Don't forget to register for our next webinar coming up on September 8th. It's using magic power modules as adjustable constant current sources. Register online at www.we-online.com/webinars. And also you can hear us every week on our new What's Up Radio podcast, WATTS. That's the What's Up podcast, available on Spotify, LinkedIn, Twitter, iTunes, Google Podcasts, everywhere you want to hear a podcast, you can listen to our webinar replays as well as our application notes from the comfort of your desk. If you're wondering about other webinars coming up, make sure you follow Worth Electronics on LinkedIn. You can also follow me. My name is Amelia Thompson. And until next time, I'll see you later.
Bye.